to take exercise 2 in homework 5. Something is done here, and we will look at the Python code first, because we are asked to read a text file in Python. And to read that text file, we have to import this pandas package, which I call PD. So that's the first thing I do. And then to read this file, it's very important that I stand in my working directory, and I do that in this spider by going here and set the working directory to where the text file is, and the text file is by me just here. I could go back and do like this, and then take this one and this one and open, and now this one is here, and then I'm on the right place and I can read the data, and here I read the data. So let's run it, and now I can go and look at the data if I want. So I could go that in the variable explorer and go to my data, and here the data is. Here's the x values and here's the y values, and now I want to extract x values and y values and store them in own vector arrays, and that's what I'm doing here. I say store in x as an array. And what do you want to store? Yes, I want to store the x's from my data, from that file. And remember, the first column there was called x, and when I'm just writing my data, it's x, it takes out the x's. So, and I make an array of the y's there. So, now we have all the, and then I'm also doing a scatter plot, and we do that. And here is the scatter plot. That's what we are going to do in 2A. So then we can go back to the exercise. And in B, we get a lot of information first. And I think it's important that we write that down, because we have to use very much of it in the rest of the exercise. So we will use following a model for the data plotted in A. And the model is yi equal beta xi plus epsilon I, for I equal 1 up to n. And where epsilon 1 and so on are independent random variables with expectation equals 0 and variance equal some number, unknown parameter, sigma in the power of 2. Okay? Remark, because the epsilon i's are random variables and independent, then, and the rest here is just constants actually, or fixed numbers, then the yi's also has to be a random, independent random variables, because they are functions of independent random variables. And that's what stands here. yi must also be independent random variables, since the yi's are just functions of independent random variables and some constants. Okay. It's two unknown parameters in the model. It's of course beta, we all see that, because that's here and we don't know it. But sigma in the power 2, we don't know either. Our estimator for beta, which we denote beta hat n, will be the minimizer of the function here. And this is actually, when we minimize this, we find the so-called least square estimator. And we are asked actually to find this estimator in B. And to find this estimator, we have to how do we minimize an expression like this? Yes, we have to derivative it and put it equal 0. So I find the derivative, but to find the derivative I just expand the square first because I'm asked to do it in the text. So then we see here that this is just a square, and I expand it, so I get yi in the power of 2 minus 2 times this yi times beta xi plus, and this last term in the power of 2, which is beta in the power of 2, xi in the power of 2. And then I let the sum sign go inside the parenthesis. So we get the sum of yi in the power of 2 minus, and 2 beta is just constant, sum yi xi plus the constant beta in the power of 2, sum xi in the power of 2. And then I use this expression to find the derivative, because it's easier to derivative this than the first one maybe. And the derivative of this is nothing else. This is just a number, so this is equal 0. Get 0. This is we are derivating with respect to beta. So all this other here is just numbers. So therefore, just as if we had the g of x equal 2x, we know that the derivative of this is 2. But now it's something else. Now it's the derivative of beta, and then we have to derivative with respect to that one. So this first got 0, this is 2 times yi xi, and this is just this derivative of this is 2 beta times this one. And then we put it equal 0 in C to find the estimator. And then I just put this term here on the other side, divide on 2, then I get this line, and then I just divide on sum xi in the power of 2, and then I get beta alone, and I get the estimator beta hat n equal the sum of yi xi divided on sum xi in the power of 2. So now I actually have an expression for beta hat. And if you remember the model here, and just think that this is 0 because the expectation is 0, we could make a straight line with this beta hat as an estimator for beta. And that is what we are asked to do in exercise 2D. We're now going to make this straight line with y equal beta hat x. Okay, and that's Python actually. So we go to Python, and first I find beta hat, which I know the formula for because I just found it here. Here is the formula for beta hat, and that's the sum of the y times the x's divided on the sum of the x's in the power of 2. Just what's written here. The sum of y times x divided on sum x in the power of 2. So then I run this, and I get a number which is 4.859. 4.58959, I mean. If you wonder, check it out. There. And then I plot xy as a scatter plot, and I have to put the line on, so I use the PLT's its plot command, and the line is the x values for the line is x, but the y values for the line is beta hat x. So then I run these two together to be sure that they get in the same plot. And there they are. So then we are in E, and we are going to show that the expectation of yi is equal to the expectation of beta xi plus, no, we are going to show that expectation of yi is equal beta xi. Okay, how do we do that? Well, yi is nothing else but beta xi plus epsilon I. Remember, that's defined here. yi is this. And since I'm asked to get something with beta xi, I just change yi with beta xi plus ei, epsilon I. So then I just take the expectation of each term, and then I get beta, because it's a constant, times the expectation of xi, plus the expectation of epsilon, which is 0, as we know from the text, and the expectation of xi, that's actually just xi, because xi also is a number, fixed number. Let's write that here. Remember, xi is a fixed number. Okay. Then we are going to show that the variance of yi is equal sigma in the power of 2. That's a little more tricky, but not impossible. We just use the formula we know from exercise 1, that the variance of something could be written as the expectation of this something minus the expectation of this something in the power of 2. Like this. So I take beta xi plus epsilon I minus the expectation of this thing, and put everything in the power of 2. And then take the expectation of this. And then I just open up this parenthesis here. So I write this as beta xi plus epsilon I minus expectation of beta xi minus expectation of epsilon I. And we remember now that this one is nothing else but beta xi from what we showed just above. And this last one is also 0. So here it stands 0, and then we have everything in the power of 2. But it's nothing much left here now. We actually got just epsilon, and this disappears, and I stand with epsilon I, and I keep the 0 now, just because it's easier to explain the next step, like this. And if we stare at this one, we'll see that this is nothing else but the variance of EI. Why is it so? Yes, because we know that the variance of EI could be written as the expectation of EI minus the expectation of EI in the power of 2. But we know that the expectation of EI is 0. So we got this. And this is what I see here. And that is the variance of EI. But we also know what the variance of EI is. Or the epsilon I say E and epsilon I. But you understand. This is just sigma in the power of 2, because that we have from the text here. The variance of epsilon I is sigma in the power of 2. That's the information we got. So that was okay. Then we can go to F. And in F we are asked to show but before I do it, we have a hint here, and we're going to use that we're going to use it. So hint, and that is define AI equal xi divided on the sum I equal 1 to n xi in the power of 2, like this, and then write beta n hat, which we know the formula for, because that's just the sum yi xi divided on the sum xi in the power of 2. But write this as the sum I equal 1 to n. And if you look at this now, you can write this as AI xi, yi. Because the AI is this one is, you can see it in here, except for the yi. So this must be correct. And then we can do what we're asked to do, show that the expectation of beta n hat is equal beta. So I do that, then I get the expectation of beta n hat, which is the same as expectation of the sum I equal 1 to n yi xi divided on the sum I equal 1 to n xi in the power of 2, which is equal the sum or equal the expectation of the sum ai yi I equal 1 to n. And we know that we can write this sum out like a1 y1 plus a2 y2 plus an yn. And then we get, and knowing that a1 and a2 and so on is just constants because they are made of fixed numbers. So I get this is then just a1 expectation of y1 plus a2 expectation of y2 plus a1 expectation of yn. But remember that the expectation of the yi's is just beta xi. So from exercise above we get that this is a1 times beta x1 plus a2 beta x2 plus an beta xn. But then we can factorize beta outside, so we get beta parenthesis a1 x1 plus a2 x2 plus an xn. And then I can write this as a sum again, which is nothing else but the sum I equal 1 to n AI xi, but this is just, if I now put in the AIs here, we know that the AIs is xi and times xi here, divided on the sum xi in the power of 2. And then we get that this is the same as beta sum I equal 1 to n xi in the power of 2 divided on the sum I equal 1 to n xi in the power of 2, and we get beta. So here, using exercise 1e, 2e, 2, we are in 2 now, 2e. So, and yes, that should be enough. And then we are going to show that the variance of beta n hat, show that variance of beta n hat is equal, what is it equal? It's equal sigma in the power of 2 divided on the sum I equal 1 to n xi in the power of 2. So this we have to show, okay? But now we use the hint. Remember, AI is equal xi divided on the sum xi in the power of 2, like this. And remember, that the variance of ax plus by, for example, is a variance of x plus b variance of y if x and y are independent. See exercise 1, exercise 1F. If you wonder. So, and these are going to use now. So then I start, so this I have to use. But we know, so variance of, so this is just something we are going to use. So variance of beta n hat is the same as the variance of the sum I equal 1 to n yi xi divided on the sum I equal 1 to n xi in the power of 2, which is equal, putting in the AIs, which is equal the variance of the sum I equal 1 to n ai yi, and then this is again the same as the variance of a1 y1 plus a2 y2 plus an yn, which is equal, and remember these a's are just constants because they are made of fixed numbers, and we get that this is following the second reminder here, that the variance of two different random variables are just the sum of them if they are independent. So, oh, here's a little, it should be a in the power of 2 and b in the power of 2 there. Of course, that's follow just following the formula for, as we know it. So this is then the same as a1 in the power of 2 variance of y1 plus a2 in the power of 2 variance of y2 plus an in the power of 2 variance of yn. And then we get a1 in the power of 2 variance to y1, that's its sigma in the power of 2, because that's an information we got from the text, plus a2 in the power of 2 times sigma in the power of 2 plus an in the power of 2 sigma in the power of 2. And then I factorize sigma in the power of 2 outside a parenthesis, and I get a1 in the power of 2 plus a2 in the power of 2 plus an in the power of 2, and then we get sigma, and this is just a sum of the ai's, I equal 1 to n in the power of 2. And if I now just put in for ai's, I get that this is nothing else but the sum I equal 1 to n xi in the power of 2 divided on the sum I write this. Actually, I have a remark here, but I do it now, like you have done it, I think, in the lectures. But this is then sigma in the power of 2, sum I equal 1 to n, xi in the power of 2, sorry, it's okay, divided on the sum xi in the power of 2, like this, but that's in the power of 2. And then we get that this is sigma in the power of 2 times the sum I equal 1 to n xi in the power of 2 divided on the sum xi in the power of 2 in the power of 2, and I can take this against this, and we end with what we wanted to have, namely that this is nothing else but sigma in the power of 2 divided on the sum xi in the power of 2, like this. And that was what we was asked to show in the top here. So then we have show that the variance of the beta m hat is this expression here. Then we are soon finished. We have the G, and here we are asked to, or we get this estimator for sigma in the power of 2, which is sigma hat in the power of 2 of the n data we got. That is equal 1 divided on n minus 1 times the sum I equal 1 to n yi minus beta n hat xi in the power of 2. And we are actually asked in Python to use this expression and the data from the text file we have read into Python to estimate the unknown sigma an. So use this expression to find an estimate for the real world actually the model for the sigma in the power of 2. Okay? So then I go to Python and I have to implement this here, and that shouldn't be too hard because we know the yi's. We know the beta hat because we found that in exercise 1D or something. Or 1, where did we actually find it? 1D, yes. And we know the xi's. So here everything is numbers. So it should be easy to implement. So we do that here. Sigma hat square is 1 divided on n minus 1. Why do I do that? That's because it stands here, 1 divided on n minus 1. And then I had to take the sum of the y's minus the beta hat times x in the power of 2, like this. Just sum of y minus beta x in the power of 2. And if I then and I have to know how I have to know the n, but here we have 100. We can see here that the x is a 100 and y is a 100 and the data frame is a 100 numbers. So the length of these arrays are 100. So therefore this, and then I can do like this, and we get something, and we could see what it is. It is actually 2.1938 and so on, and that's here. Okay, and then so C Python, and then H, and H is the standard error of an estimator. It's the square root of the variance of the estimator. Okay. The standard error of an estimator is the square root of the variance of the estimator. So therefore, the standard error of beta n hat is, and we just shorten it down to standard error like SE, of beta n hat is, as we just said in the text now, is the square root of the variance of the beta n hat. But if we write this a little more out, we know that the variance of beta n hat, that is equal, we have found that higher up here, we found it here actually. This is the variance of beta n hat. This is sigma n divided on this sum of xi's in the power of 2. So this is the same as the sigma in the power of 2 divided on the sum xi's in the power of 2. But the problem here, we do not know the sigma in n. So we rather use sigma hat in the power of 2 as an estimate for sigma in the power of 2, and then we easily find an estimate for the standard error beta n hat. So then I get that an estimate of this standard error is equal, plotting in now sigma hat n in the power of 2 here. It's may hard for someone to follow now. So we get standard error beta n hat is equal the root, and this sigma hat squared, we have found an expression for that just in G. Here we have this expression for sigma hat n in the power of 2. So that is what I'm filling in here. So this is just then 1 divided on n minus 1. The sum I equal 1 to n yi minus beta hat n xi in the power of 2. So this one is this one, and divided on the sum xi in the power of 2. It should be okay. I equal 1 to n, and then I just have to implement then in Python. Find this in Python. Find this in Python. So then we go to Python, and here I just showed you the formula for the standard error of beta hat n. How we could find an estimate for that standard error. That's by filling into this formula. And that is nothing else but the sigma hat squared divided on the sum of the x's and then the root of all of this. So therefore I take the square root of this sigma hat square, which I actually have found here in the line in 2G, and divide it on the sum of the x in the power of 2. And then I got this one. So I take what I found in 2G, that is this one, I divide it on the sum, but first of all I have to take the square root of everything. So then we can run this code and see if it works. Hopefully it does. Well, let's see if we get the same result here. We should. 0.2546, etc. So if I haven't done anything wrong here, it should be okay. Yes. So that was exercise 2, and then we take exercise 3 in the next video. Thank you.